Hi, what's up, you guys? So, in our previous videos, we did problem number 1 and problem number 2. And in this video, we'll do problem number 3. So, this one right here. Okay. Now, before we jump right into the problem, let's quickly do our quick revision for the steps like we have done for question number 1 and question number 2. And like I said earlier, that these are the steps that we'll be using in all the problems of section 4.1, okay? So it's very important that we really understand and somewhat just memorize it, the steps, okay? All right. So like I've seen earlier, that our step 1 was basically substituting the power series expression for y and y prime. Oh, it's supposed to be a y prime over here. Well, technically it is right too. Like in questions, we'll see that we'll have y double prime, and we'll talk about that when we deal with those questions. But for now, we can just just find the power series expression for y and y prime, and then plug them into our differential equation. Then we need to match the powers of x to x to the power n. So we'll have our power series and we'll try to match them to x to the power n. Then we'll try to shift our starting indexes, okay? And again, I've mentioned before that we'll always pick the starting index, which is like the larger starting index, okay? So if we have, let's say, if one of our power series starts from n equal to 2, so the other power series present will also have to start from n is equal to 2, okay? All right. And then once we match our exponents to x to the power n and we shift our indices, then we can combine our power series into 1. And then we can solve our coefficients using our recurrence relationship. And then finally, after determining those coefficients, we can write our final solution, which will be in this form right here. Okay, so these are the steps that will follow for question number 3 here. Okay, all right, so let's now get into that. So this is my problem number 3, which I copied earlier. And now we'll try to find our solution. And in our question, it says that we'll generate few terms for that too. Okay, so let's now substitute our power series expression into our differential equation. So our y prime is summation from n equal to 1 to infinity a sub n times x to the power n minus 1. And then I have a plus, then I have 1 minus x squared times our y, which is summation n equal to 0 to infinity a sub n x to the power n equals x. Okay. Now, I have to multiply. I have a 1 minus x squared on the outside, right? And I'll try to distribute that with our second power series. So let's go ahead and do that. So I have my summation n equal to 1 to infinity a sub n times x to the power n minus 1. And then first I'll multiply my 1 with my second power series. So it's just going to be summation n equal to 0 to infinity a sub n x to the power n. Then I have a minus x squared. So now I'll multiply our minus x squared with our second power series. So I end up with summation n equal to 0 to infinity a sub n x to the power n plus 2 equals x. Now, we have talked about this earlier. The only reason that our exponents adds up, because by rules of exponents, we know that if our bases are the same, that means their powers adds up. So we can see that our base is just an x, right? They both are x, that means their exponents adds up. So it's going to be n plus 2. Okay? All right. So we have successfully done our first step, which was substituting our power series representation into our main differential equation. Okay, now our second step would be I'll try to match my exponents to x to the power n. So I'll try to make this, this, and this to an n. And we can already see that my second power series already has an n. So that means I don't have to do anything with it, right? So we only need to change our first power series and my third power series. So let's go ahead and do that. So first I'll try to change my first power series. So I will use a red colored pen for my first power series, okay? It's going to be summation n equal to 1 to infinity a sub n times x to the power n minus 1. And I know that it needs to get transformed to x to the power n, okay? Now, if we look, we can see, if we can observe clearly, that if we just add 1 to it, that means our -1 and +1 gets canceled. So I'm just left with the power n. And that's exactly what I wanted to do, right? So all I need to do is just add 1 to all my n's. So that means my a sub n becomes a sub n plus 1. And my n here becomes n plus 1, okay? And in our previous videos, we also talked about how if we increase our n's in my power series by a certain amount, then my starting index decreases by the same amount. So since I have increased all my n's by a 1, that means my starting index would decrease by 1. So now, instead of starting from n equal to 1, it's going to start from n is equal to 0 to infinity. Okay? So that's how I've transformed my first power series to x to the power n. Okay. So let's go ahead and now change for my third power series. So I have summation n equal to 0 to infinity a sub n times x to the power n plus 2. Okay. Now I'm going to transform this to x to the power n again. So again, if we carefully observe, if we subtract 2 from this power right here, we will get just an n. Okay, so all we need to do is subtract 2 from all my n's. So that means my a sub n becomes n minus 2. All right, so again, since all my n's in my power series decreased by 2, that means my starting index increases by 2. This means that instead of starting from n is equal to 0, it's going to start from n equal to 2 to infinity. Okay, so I have also transformed my third power series. So let's go ahead and copy that. Okay, rewrite our power series into our transformed ones. So now my first one becomes summation n equal to 0 to infinity a sub n plus 1 times n plus 1 times x to the power n. And then I have my second power series, which stays just the same because it already has the power n, so we don't do anything with it, right? So I have a sub n x to the power n. And then I've changed my third power series. So before it was n plus 2, now it became just an n. So it starts from n equal to 2 to infinity a sub n minus 2 times x to the power n equals x. Let's not forget what we have on our right hand side. Okay, so this is how it looks. So we have fulfilled the first condition, which was transforming these exponents to just x to the power n. Okay, now again we have to fulfill our second condition, which was to make sure that these starting indexes also match, right? And we've also said that we'll always keep the starting index which has a bigger number. So we're always going to keep the bigger starting index, which is n is equal to 2, right? So That means I want to start my first starting in my first power series to 2. I want to start my second power series to also a 2. Right? So let's go ahead and do that. So I have my summation n equal to 2 to infinity a sub n plus 1 times n plus 1 times x to the power n. And then I also want to start my second starting index from 2. So I have summation n is equal to 2 to infinity a sub n x to the power n. And then I have my third starting index, which is already in 2. So do not have to do anything with it. Okay. So we have, made sure that our starting indexes are the same. However, if we start them from 2, we are losing some terms, right? We are losing the term that we have gotten, we could have gotten if my n was equals to 0, right? So that means I'm losing my n equal to 0 and n equal to 1 for my first power series, and I'm losing n is equal to 0 and n equal to 1 for my second power series. And clearly I cannot lose them, right? I have to include them. So like I mentioned in my steps, all I need to do is just explicitly write them. So just separately write them out with these expressions. So let's find out what my n equal to 0 and my n equal to 1 would have been. So let's do that for my first power series, which is this one right here. So when n is equal to 0, we get a sub 0 plus 1 times 0 plus 1 times x to the power 0, which is a sub 1. And then when n is equal to 1, so I have a sub 1 plus 1 times 1 plus 1 times x to the power 1, which is 2 times a sub 2x. Okay, so these are the two terms that I would have missed if I haven't included them. So let's include them real quick. So I have plus a sub 1 plus 2a sub 2x. Okay. Then I also need to include the first two terms for my second power series, which is this one right here. So when n equal to 0, so I have a sub 0, x to the power 0, which is just a sub 0. And then when n is equal to 1, so I have a sub 1 and x to the power 1. Let's just have a sub 1 and x. So let's include that over here as well. So I have a sub 0 plus a sub 1 times x. And then we can write equals our x. Okay. So that means we have also included the terms that we would have lost, right, if we haven't included them. Okay. So now I have explicitly written the first two terms of my 2 power series, right? So now it's my fourth step, which was basically finding the coefficients. So now we got to find the coefficients for a sub 1, a sub 2, a sub 0, a sub 1 over here, these coefficients right here. So I need to now solve my coefficients. Okay. Now I want to rewrite this expression right here, okay, so that the powers of x are an increasing term, okay, and also combining our 3 power series into 1, okay. So let's go ahead and rewrite that. So I have a sub 0 plus a sub 1 plus a sub 1x plus 2a sub 2x plus combining all these 3 power series. So I have summation n equals to 2 to infinity, taking out x to the power n as common. So I have a sub n plus 1 times n plus 1, then plus a sub n minus a sub n minus 2, and then equals x. Okay, so this is how it looks like, and clearly we can see that we are doing a good job so far. And now I want to find what my coefficients are. Okay, so now, like I said, the first thing we do is we look at the constants. That means the ones that doesn't have an x attached to it. So if we look carefully, we have already written out the two terms that's without an x, okay? So I have a sub 0 plus a sub 1. Now we are going to look at our right and see if there's any coefficient or without the x, or I could say that is there's any constant, right? Because we know that constant means that there's no x to it. And I can see there is no constants, or there's no coefficient with x to the power 0, like without any x. So that means a sub 0 plus a sub 1 is actually a 0. Now, in our previous videos, we have seen that my a sub 0 is mostly arbitrary. That means that this could have any value, right? And we can only determine this value. That means this value can only be determined if I was given an initial condition in solving these differential equations, right? So basically what I'm saying is that if I was given y of 0 value, okay? So a sub 0 can only be determined if, I was given y of 0. And since I'm not given any initial condition values in this entire exercise of 4.1, that means I'll always treat my a sub 0 as an arbitrary number, okay? That cannot be determined with whatever we have, okay? So if that is the case, then I can isolate my a sub 1, which is basically negative a sub 0. Okay. All right. So now let's look at our terms where our power of x is 1. So basically this one right here. So I have a sub 1x plus 2a sub 2x. So that means if I add up the coefficients, I have a sub 1 plus 2a sub 2. So this is the coefficient for x, right? When the power of my x is 1. So this is the coefficient. So now I'm going to look at my right and I'll see what is the coefficient for x, and I can see it's just 1x. Okay, so that means my a sub 1 plus 2a sub 2 is basically 1. Okay, now I'm going to isolate my a sub 2. So I have 1 minus a sub 1 divide by 2. Okay, and from here, we already know that my a sub 1 is basically negative a sub 0. So if I substitute my a sub 1 with my a sub 0, I get 1 plus a sub 0 equals 2. So this is my coefficient for a sub 2. Okay, so I've got my a sub 0, which is an arbitrary number. I have my a sub 1 right over here, which is negative a sub 0, and then I have my a sub 2, which is 1 plus a sub 0 divided by 2. Okay, so I've got my coefficients for a sub 0, a sub 1, and a sub 2. So now let's go ahead and find the rest of my coefficients over here. Okay, now again, thing to observe that the only coefficient I have at my right is for my x, right? When my power of x is equals to 1, right? When the power right here is just 1, okay? And we don't have any other coefficients of x, right? Or we don't have any constant either, like we have seen when we were trying to find the value for a sub 1. So the only coefficient we have is for x to the power 1. That means any other powers of x, we don't have any coefficients. That means for any greater powers of x, the coefficients are 0, right? So this basically means that this entire thing is a 0, because if you look that our series starts from n equal to 2, right? That means it starts from n equal to 2. That means x going to be x squared, right? So it's going to be x squared, then x cubed, x fourth, all the way up to infinity. So whatever the power is, it's always going to be 0 because there is no coefficients at my right-hand side, okay? So that means I can write a sub 1 times n plus 1 plus a sub n minus a sub n minus 2 is equal to 0, okay? Now, I'm going to find my recurrence relation, which is basically what I'll be needing to solve for my coefficients, okay? So I'm going to isolate my a sub n plus 1 so that I have a sub n minus 2 minus a sub n divided by n plus 1. So this is my recurrence relation, which is for n greater than or equal to 2. So when n is equal to 2, write that, okay. So I have a sub 2 plus 1, which gives me a sub 3, which equals a sub 2 minus 2 minus a sub 2 by 2 plus 1. So I have 1 by 3, a sub 0 minus a sub 2. Okay, so I know that my a sub 0 is arbitrary, right? So it stays the same. And I know my a sub 2 is 1 plus a sub 0 by 2. So let's substitute that over here. So I have a sub 0 minus 1 plus a sub 0 divided by 2. Now, if you simplify that, you'll get 1 by 6 a sub 0 minus 1 by 6. And notice that 1 by 6 is basically the same thing as 3 factorial. Okay, so I have a sub 0 minus 1 by 3 factorial. Okay, because we all know that 3 factorial is basically 3 times 2 times 1, which is 6. So it's the same thing, like just like rewriting this. Okay, so that is what we have for a sub 3. So now let's go ahead and find for a sub 4. So I have n equals to 3. So I have a sub 3 plus 1, which is a sub 4, equals a sub 3 minus 2 minus a sub 3 by 3 plus 1, which is 1 by 4, a sub 1 minus a sub 3. Again, we know what our a sub 1 is, which is basically negative a sub 0. So just plugging in those values. And then my a sub 3 is this one right here. So I can write 1 by 6 a sub 0 minus 1 by 6. Okay, let's not forget the brackets. We want to always give the brackets out so that it gets less confusing. Okay, sometimes if we do not include the brackets, we can mess up the signs. So I would recommend always using the brackets when you're trying to plug in something into something. Okay, now again, if we simplify them, we get negative 7 by 24 a sub 0 plus 1 by 24. And you will also notice that by 24 is basically 4 factorial. So 4 factorial is 4 times 3 times 2 times 1, which is 24. So I can already tell that a factorial must be present in this pattern. Okay, it does happen in my pattern. Factorial a sub 0 plus 1 by factorial. Okay, just draw a box just to kind of not get lost. Okay, So now let's do for n equal to 4. So I have a sub 4 plus 1 equals a sub 5 equals a sub 4 minus 2 minus a sub 4 by 4 plus 1, which is 1 by 5 a sub 2 minus a sub 4. Okay, so again, we will need our values for a sub 2 and for a sub 4. So if I plug in those values, okay, just going to write the, okay, yeah. All right. So if I plug in my a sub 2 and my a sub 4, you will notice that I get 11 by 120 plus 19 by 120 a sub 0, which is basically the same thing as 19 by 5 factorial a sub 0 plus 11 by 5 factorial. Okay, you know what? Let me write the a sub 0 first, okay? Okay, so I have 19 by 120 a sub 0 plus 11 120. Okay, so yeah, if we simplify that, that's what we get for my a sub, for my a sub 5. We draw a box, okay. Then let's do for n equal to 5. So I have a sub 5 plus 1, which is a sub 6, equals a sub 5 minus 2 minus a sub 5 by 5 plus 1, which is 1 by 6, a sub 3 minus a sub 5. If I plug in for my a sub 3, which is this one right here, and then my a sub 5, which is this one right here, we get the value 1 by 720 a sub 0 minus 31 by 720, which is the same thing as 1 by 6 factorial a sub 0 by 31 by 6 factorial. Okay, all right. So I think we do have an idea of my pattern. So since we have already found the first 5 terms of my solution, so let's go ahead and write out the terms, okay? Write out my final solution. So I know a sub 0 stays a sub 0 because, like I said, that it's an arbitrary number. So, you know, it doesn't change anything. We do not know the value until or unless we have an initial value. So it stays as it is. Then I have my a sub 1, which is this one right here. Let me go up. This one right here, which is negative a sub 0. So let me write a sub 0 plus x. And then I have my a sub 2, which is, if I simplify that, I have half plus half a sub 0. And I know 2 is the same thing as 2 factorial, so I could include that as well. So I have sub 0 plus half. Okay. And then I cannot forget my x squared. And then I have my a sub 3, which is 1 by 3 factorial a sub 0 minus 1 by 3 factorial. So I can write 1 by 3 factorial a sub 0 minus 1 by 3 factorial. Okay, and then let's not forget my x to the power 3. Then I have my a sub 4, which is negative 7 4 factorial a sub 0 plus 1 by 4 factorial. And then let's not forget my power 4. And then plus I have my a sub 5, which is 19 by 5 factorial a sub 0 plus 11 by 5 factorial. x to the power of 5. Okay, so I think we have our first 5 terms. So what I want to do is I want to further simplify that. So basically I can see that there is an a sub 0. So I want to separate my a sub zeros so that it looks nicer. Again, this is not necessary. You don't necessarily have to do that. But if you still want to make it look pretty, you can. So I want to make it look pretty, okay? So I'll try to isolate, I have to separate, I want to separate all my a sub zeros. So if I do that, I have 1 minus x plus 1 by 2 factorial x squared plus 1 by 3 factorial x cubed minus 7 by 4 factorial x4 plus 19 by 5 factorial x5 and so on. And then separately write out the terms without the a sub zeros. So I have 1 by 2 factorial x squared minus 1 by 3 factorial x cubed plus 1 by 4 factorial x to the power 4 plus 11 by 5 factorial x to the power 5 and so on. Okay, so this is my solution. Now, hope this helped you guys out. Hope you guys enjoyed this video as much as I enjoyed making them, and I will see